Okay, so today we'll talk about the electric field due to a charged disk. So it's a bit different from the last one. Last one is actually a charge ring, and now it is a solid disk. So actually, we still using the same technique. We try to separate a disk into many infinitesimal unit, and then we calculate the E field generated by that unit, and then we sum all of them together. And actually, summing in finite term means we need to use the integral to do this. And since we have this result, so let us make use of this result, actually this one, so that as long as we have many charge ring with different radius, and then we can from 0 to capital R to capital R, this one, this with a radius of capital R. So as long as we have many ring with different radius from 0 to capital R, then consider all of them, then you will form a solid disk. Actually, you may ask whether we can separate it like actually, suppose we have a disk. We try to separate it like this, with many rings. Actually, suppose we know the E field generated by each ring, and we can sum of them together. Actually, you may ask whether we can separate like this. This may be straightforward, but actually, if you can write an integral according to this is a Cartesian coordinate. Actually, you should be able to get the same answer if you write the equation correctly. But it may be quite difficult to calculate this integral, or maybe not calculatable. An example is something like when you learn the calculus, when you try to calculate the area of a circle. So in primary school, you know that the area of a circle is nothing but pi r squared. And if you try to calculate it using the calculus in Cartesian coordinate, it will be something like this. R squared minus x squared dx, something like this, right? I suppose you have learned the calculus. And actually, you should use the U substitution. You may assume U equals no, x equals U no R. R sine theta, something like this, and then you substitute there, and you will also have dx equals R cosine theta d theta, and then you change the limit of this integral, and then you know that the area of this circle is actually pi r squared. If you really use the polar coordinate, actually it will be more simple. Actually, if you use the polar coordinate, you cut the circle like this, and then you integrate like that, and then actually the area will be something like dA, and actually dA is something like this, r d theta, something like this. And actually you just have something like this, and d theta is something like from 0 to 2 pi. Yes. So this one, for the first term, you will get r squared over 2, and for second term, you get 2 pi. So you end up with pi r squared. So this is an example to show that if you use different coordinate to calculate the same thing, then the step may be quite different. The lower one would be much easier than the first one. You see that if you use the polar coordinate, then actually the variable can be separated into two parts, and then this double integral will be just two single integration, and then you get the answer. But this one, you may need to use something like the U substitution, and then do many more steps to do that. So actually, this case is something like this. You separate this solid disk into a many ring, and then you integrate them together. So actually, for the last case, we have this one. So first term is the constant, the k, and then the charge on the ring, and then z is the distance on the center, and then the distance from the center to the point you concern. And then this one is another term, the radius of the disk, and then the distance. So here, the total charge means Q means the total charge of the disk, not the ring. So we change Q into dQ in this case, and then E into dE in this case. So which means that the dQ is actually the charge on the ring in yellow color, and then it generates the E field. We call it dE, and then we try to integrate the dE over the radius from 0 to capital R to capital R. So, any question? So that this with radius capital R and uniform positive charge, and the ring shown has a radius small r, and actually the width of this wing is dr. So okay, so let's move on. Actually, we need to do this integration, and then we make a small substitution. Actually, we know dq will be the density times the area of this ring. We actually assume this is very thin. The height of this disk is 0 actually. And sigma will be the surface charge density, different from the last case, linear charge density. So the SI unit of this sigma is different. This is C over m squared. So for the area of this ring, is actually 2 pi r times dr. Which means that suppose this ring, the height is dr is very small, and then you try to cut it. You can assume it that you flatten it. It will something like a rectangle. So a rectangle, the width will be 2 pi r, which means the circumference of the circle, and the height of this rectangle will be dr. It may be difficult to imagine, but it was something like this. The width is 2 pi r, the height is dr. So it is actually area of a rectangle. So we substitute dq to be this term to here, and 2 pi and 4 pi are cancelled. Is it pi and pi are cancelled? So we have 4 epsilon naught, and sigma z is here, and then 2r dr. Actually, we leave this term. Actually, we need to use the chain rule. So we need to calculate the overall E field generated by the whole disk. So we integrate dE, and we actually substitute. We actually substitute this term to here. Actually, substitute that this term to here, and you can see that 2r dr is actually this term. dr square equals 2r dr. Just a simple derivative, right? So z square is actually a constant to r, so we add a constant to here. So actually this one is actually this one. Okay, so this term to 3/2 power in the denominator, so that we make it minus 3/2 power in the denominator. So the red term like this, the green term like this. Okay, so so this one is something like you integrate a polynomial. You can just regard this is a term. Maybe you can call it x, but I do not make this substitution here. Maybe you just imagine x is r squared plus z squared. So this is actually you integrate x to 3/2 power dx, something like this. So this integration should be very easy. You only need to add one. So it is minus 1/2 power, and then you divide this term. So this is actually the integration of this one, and then don't forget the lower and upper bound. And then we need to substitute r into here and 0 into here and subtract them. So here we have a negative sign, so 0 substitute into here. We will get 1/square root of z squared, and then minus r substitute into this term, and then we have 1/square root of z squared plus r squared. So finally, we just factor out z, because square root of square root of z squared is z, and then we can cancel with this z, and then we just multiply z into here and here, so that we have z here. So any question for this? Okay, so we get this result. And actually we assume that the radius of this disk is infinite. If we assume the radius of this is infinite, which means that the whole plane expand to infinite far away, then actually this term will be simplified like this, because r tends to infinity and z is finite, so this term will be 0, this term will be 0, so this whole bracket will be 1, and then so it reduces to this case. Although it seems that practically it's not reasonable to have a infinite large plane with charge, but actually this term can approximate some case, and actually we'll see this term in next chapter and also in chapter 25. When you talk about the capacitance, we'll use this approximation. And in the next chapter, the Gauss law, we will use the Gauss law to almost get the same result using the Gauss law. And later you will see it again. So it's nothing but assuming that this has an infinite radius. Actually, at that case, even though the disk is not infinitely large, but if you consider the point close to the plate, then it will actually approximate similar to it. It's something like if the disk is somewhere maybe close to here, it will be something like that. If z is quite large, far away from this plate, then you need to minus this term. And actually, this is very interesting, which means that the E field is uniform. It is not related to the distance, related to the position of the point you concern. Sigma is the density, the surface density of the charge, and epsilon 0 is the permittivity, which is also a constant. So the E field is a constant, which means that if you have a large plate, then you can generate a constant E field. So next, we talk about the point charge. The point charge in an electric field. So if a particle with charge Q is placed in an external E field, an electrostatic force acts on a particle, F equals QE. So at the beginning of this chapter, we define the E field by the electrostatic force. And actually here, now we know that we can generate a constant E field. So if we place another charge in this constant E field, of course it will have a force. So we just reverse this. So the electrostatic force acting on a charged particle located in an external E field has a direction of E if the charge of the particle is positive, and has the opposite direction if Q is negative. So we should already know about it. E field should match the positive charge. So if it is a negative charge, the direction should multiply by a -1, so it will be in the opposite direction. So here, in this case, you should concern about this graph. Maybe I can zoom in. So here we have This is the ink box. Suppose G is green. G means green, and then C is means charge. C means charge. So this briefly tells you the mechanism, the simplified mechanism of a printer. So actually, you have the ink. Maybe this is green, or maybe it is blue, or red, or dark, or black. So no matter what this color is, so you try to add some charges on a drop of ink, and then here we'll have a E-field, and of course, if this is so the E field points to the downward, so the charge will be negative, so it will have a force pointing to the upper direction, which means that if this ink is already originally injecting to the right side, and then it will have a force going to the upper side, so the ink will go in this path, something like this. Okay, so the inkjet printer drop shot from the generator G, or maybe it mean G, mean the generator, not green. Receive a charge in the charge unit, and input signal from a computer control the charge, and thus the effect of the field on where the drop lands on the paper. So actually, changing the E field may not be so convenient. So we try to change the amount of charge. If the charge is larger, then the ink will go to an upper position on the paper. And if the charge is smaller, then it will go more straight. If the charge is 0, then it will directly go in here. The mechanism is simply like this. So we have a sample problem. So so the deflecting plate of the inkjet printer with superimposed coordinate axis, an ink drop with a mass and a negative charge of a magnitude Q enter the region between the plate, initially moving along the x-axis. So this is the x-axis, and initially moving along the x-axis with the speed like this. The length of the plate is 1.6 centimeter. The plate a charge, and thus produce an electric field at all points between them. So we assume the field is downward directly between this area, between this area. So we assume the E field is uniform in this box, and has an amplitude 1.4 times 10 to 6 Newton per Coulomb. What is the vertical deflection of the drop at the far edge of the plate? The gravitational force on the drop can be neglected. Okay. So actually the time t for the drop going from this side to here will be 0.016 over 18, because so L is 1.6 centimeter, and actually the vertical direction, the horizontal speed, the speed in x direction is 18 meter per second, and the E field is pointing downward, so the force always pointing downward. So the charge should be going in the x direction with a constant speed. So T will be something like this, and it is actually 8.89 times 10 to minus 4 seconds. So next, F equals QE. F equals QE. Q is 1.5 times 10 to minus 13. Maybe I should make it capital Q. Capital Q times the E field is 1.4 times 10 to 6 times 10 to 6. So it should be 2.1 times 10 to minus 7 Newton. So maybe I add the page in between. So okay. So actually, we know that the force. So the vertical velocity, will be the acceleration times the total time, and oh, not this. Yeah, pretty strange. So actually, y should be 1/2 a t squared. I suppose you should learn it in high school. So actually something like this, and a equals f over m, the Newton's law of motion, the Newton's second law of motion. So 2 times 1 times 10 to minus 7 times 8.89 times 10 to minus 4 over 2 times 1.3 times 10 to minus 10. 10 to minus 10. Yeah, the mass 1.3 times 10 to minus 10. So this is actually 6.4 times 10 to minus 4 meter. Or maybe you can write it as 640 micrometer. So in the exam, you can choose this one or that one. In the textbook, it uses 0.64 millimeter. It is well. Usually, when we use the prefix, this number will be around will be between 1 to 999, between something like this, like 999, less than 1000. But this is actually okay. Well, but don't make it 0.000 millimeter, 64 millimeter. This is not so good. And for the scientific notation, like this number should be between 1 and 10. Should be between 1 and 10. Don't make it 0.64 times 10 to minus 3. This is not so good. Okay. So any question for this example? Okay, so we talk about the dipole in an electric field. Okay, so the torque on an electric dipole of dipole moment P, when we introduce the dipole moment, we also define a variable regarding to the dipole called the dipole moment. P equals QD. And actually P is a vector. The direction is from the negative charge to the positive charge, this direction in this green arrow. So when placed in an external E field is given by a cross product. So it will has a torque on this dipole, and actually the torque is P cross E. So this is the cross product. When you only consider the magnitude, it is the magnitude of P multiplied the magnitude of E times the sine theta. Theta is the angle between the P and the E and the E. And for the cross product, you should use the right-hand rule in this clause. So actually, the direction should be P cross E. So into the page. So it is demonstrated here. P should be point to this side, E onto the right side. So the top is into the page. The cross means into the page. Because in the E field, so this is a positive charge, and the E field point to the right hand side. So there will be a force dragging this one to the right side. However, this is a negative charge, and the E field is point to the right. So there will be a force dragging this one to the left side. So in this case, this one will so there will be a force dragging this side to the right side, and this one to the left side. So we do something like this. Actually, it will be some swinging like this, and then going backward, something like this. It will be a simple harmonic motion. Going back and forth. If it is originally stationary at this way, then it will be swing or something. It will be something like this. So there will be the energy conservation, the mechanical okay, energy of conservation. So the potential energy will change to kinetic energy, and then going back and forth, something like this. So it will be a simple harmonic motion. And actually, the potential energy U associated with the dipole moment will be something like this, which is a inner product. So it is the dipole moment dot the E field. Theta is actually the same definition, and here we have a cosine theta, which means that this one is actually the area between this vector and this vector. Something like no. Area is actually the outer product. Inner products mean you project this vector onto another one, and then so you have the inner product. And actually, we have a minus sign, which means that if the dipole moment and the electric field have the same direction, which means that the potential energy is the smallest case, and if it is in reverse direction, then the potential energy is the largest case. Which means that suppose the dipole moment, suppose this one is the positive side, then there will be no potential energy at all, and it will be remain stationary at this position. And if it is something like that, then it will have the largest potential energy, and then it will be something like and then it will swing a lot. Any question? Any questions? Okay. So we have two additional examples for this chapter. Okay, so the first one, so a clock face has negative point charge -q, -2q until -12q fixed at the position of the corresponding numeral. The clock hands do not perturb the net field due to the point charge. At one time, does the hour hand point in the same direction as the electric field vector at the center of the dial? Induced symmetric. So actually, for this one, okay. So for this one, we actually have a clock like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Something like this. Okay, this is 5. So we can actually separate into two parts. Maybe I mentioned it a bit. So for 1 we have -q. For 2 we have -2q. Until this is -12q. Okay. So actually, we can separate into two parts. The first one can be minus Q, minus 2Q, minus 3Q, until minus 6Q, and then this one still minus Q, minus 2Q, minus 3Q, and until minus 6Q. So the first part will be something like this, and then the second part, because for this side, it is already all the charge of this part. So we have 0, 0 on this side. And actually, if we subtract this side by this side, then we will have minus 6Q, all the way to here. Minus 6Q. Okay. Something like this. So we have 6 minus 6Q from 7, 8, 9, 10, 12, 11, 12. And for this part, we can see that this one will generate a E field at the center in this direction. And this minus Q will also generate a E field in the opposite direction, but with the same magnitude, right? So these two can be cancelled. And likewise, for minus 2Q, they generate E field, but cancel, until here also cancel. So for the first one, for the upper one, it will actually generate a E field equals to 0 at the center. Only consider the point at the center. So for the lower case, we have minus 6Q from 7, 8, 9, 10 to 11. So actually, the E field generate at the center will actually point to this direction. Actually, between 9 and 10. Actually, between 9 and 10, and actually halfway of it. So the answer will be 930. Okay.有没有问题？没有问题，我们继续。Okay, so this is the last example in this chapter. So suppose you design a apparatus with a uniform charge disk of radius r to produce a E field. The field magnetic is most important along the center perpendicular axis to the disk. At the point P, at distance 2r. Actually, the r should be the radius of this disk. So cost analysis suggests that you switch to a ring of the same outer radius r, but the inner radius r over 2. So this one, for this one, outer radius capital R, the inner radius is r over 2. Assume that the ring will have the same surface charge density as the original disk. If you switch to the ring, by what percentage will you decrease the E field magnitude at P? So actually, we call this. So we actually call this one A. We actually call this one A. So E generated by A will be sigma over 2 epsilon 0, 1 minus 2R. 2R is actually the Z. So 2R squared plus R squared. So this is actually the E field generated by this disk at point P. And actually it should be sigma over 2 epsilon 0, 1 minus 2 over square root of 5. So for the right hand side case, we can actually have the same E field, but we need to subtract the E field generated by the middle part. So actually, we can calculate the E hollow part, which means that it will be sigma over 2 epsilon 0, 1 minus 2R over square root of 2R squared plus R over 2 squared. So the difference is we consider the hollow part 空心的部分 hollow part with a radius R over 2, so that this term will be R over 2 instead of R. So here it will be sigma over 2 epsilon 0, 1 minus 4 over square root of 7. So actually, the percentage reduced will be E hollow over EA, which is actually 28.3%. 28.3%. Suppose you substitute this number and this number to here, then you find it is 28.3%.